someone get me started. What is accuracy? Where we got? Mustafa.
This is like how close you can get to the correct target.
Yes. So it's how close you get to what you should be getting.
Sorry. My alarm.
So how close?
Stop.
Is it one of those you talk to and it does what you say? How close you are to what you should get. Okay, good. That's exactly what accuracy is. It's how close we get to what we should be getting. Okay? And you may know what that is and you may not know what it is. You may not know the value, you're trying to figure it out, or you may know what you should be getting and you're trying to confirm that that's what you get. Okay? Either way is fine. B, what is it important? Why do we need to know what accuracy is? This one's kind of one of those, so easy, it's hard. Elijah, what do you got? Yeah, exactly. So the closer you are, the more reliable it is. So let's say you're trying to figure out whether whether the force of gravity affects a pendulum swinging back and forth. Well, in order to figure that out, you need to know what gravity is. So you do an experiment to figure out what gravity is. Well, gravity is 9.8, and let's say you're getting 9.7 for your value. Well, that is accurate. You're getting close to what you're expecting to get, which means whatever you get for your experiment should be valid in understanding if gravity affects the pendulum or not. So that's kind of the idea behind doing these measurements, trying to figure out how close you are to what you're getting and therefore how reliable your values are going to be. All right, excellent. Number 2, precision. What is precision going to be? Dominic? Yes, I like that. How consistent your data is, how consistent your measurements are. Now, that doesn't mean getting the exact same number every time. It means getting close to the same values every time. So 13, 14, 12, 13, 17, 11, like getting around the same value. Not necessarily having to be the same, but getting around that same value. So why does that one matter? That one's not quite as obvious as accuracy. We know accuracy is, we need to be getting the right answer, otherwise what's the point of the experiment? But why is precision important here? Why should that one matter for us? Yeah, Mustafa.
To see if your data is like consistent or if it needs like changing.
Right. If it's not consistent, then how do we know we're accurate because we did it right or we're accurate because we got lucky, right? Consistency is important to make sure that you're doing it correctly. We want to get the right answer, but we need to make sure we're doing it the right way. So why is it important for precision? It confirms that we're doing the experiment correctly and not getting lucky. Okay, so let's visualize this, thinking about Olympic archery. Okay, so the Olympics are here. One of the events is archery. So in archery, you're trying to score the most points, and you do that by hitting the center of the target. Okay, so there are 4 different things you could be. You could be accurate and precise. You can be neither. You can be accurate but not precise. Or you could be precise and not accurate. So let's look at each of these. If you're accurate and precise, you're going to hit the center of the target every single time. Again, you're not necessarily hitting the exact middle, but you're getting in the center almost every time. Okay, this is what people at the Olympics are. They are accurate and precise. They're hitting the same spot every time, and they're generally hitting close to the center, which is what they want. Sometimes they miss, but for the most part, they're getting close to where they are. So sometimes there may be one random thing. It's called an outlier. You basically ignore it. In the Olympics, almost everybody has at least one of these. You basically just ignore it and just keep going. If you're neither, it's just all over the place. Like you're just hitting around. Maybe you're way off at some. There's just there's no pattern, and on top of that, you're not getting close to the center. Okay. So just all over the random place. Okay, if we're accurate but not precise, we're hitting the same spot every time, but we're not hitting the spot we want to hit. So this was that example of your sights are off on your bow, and so you're hitting the same spot you're aiming at, but your aim is incorrect. Yeah.
That's accurate, not precise.
Oh, did I switch them around?
Yeah.
Thank you, I appreciate it. I said them right, but I put it in the wrong one. That's my bad, thank you. Okay? So, precise but not accurate. We're hitting the same spot every time, but we're not hitting where we want to. If we're accurate but not precise, we're not being consistent, but occasionally we're getting the right thing, and we're kind of clustered around the right answer, but we're not consistent with what we're getting. So if this was the case, there's no chance you're going to win. You're going to hit the target sometimes, but for the most part, you're getting all over the place. So your score is going to be lower than everyone else's. Okay, and you can see that's just as bad as this, right? This is also going to give you a really low score. So just because you hit the target randomly doesn't mean you're doing it right. That's why you need both accuracy and precision. You need to make sure that you're getting the right answer and you're getting the right answer consistently. Otherwise, that's why we don't do one trial. Because if you do one trial, you could get lucky once, but you don't know that you're doing the experiment right, which means every other measurement you do may be completely off. And so you're saying you're getting the right answer, but you're actually not, because you got lucky one time. Okay, any questions on 1 through 3 for me? Sweet. Okay. Number 4, using data, how do we determine if we are accurate? So, just looking at numbers, just using the numbers we have, how do we figure out if we are accurate? We use something called percent error. And that tells us what percent off are we from what we should be getting. Now, this only works if we know what the answer should be. We don't know what the answer should be, we can't do this if we're trying to figure out the answer. But if we know what the answer should be and we're testing to see that that is correct, then we can figure out how close we are to what we need. And the equation for that is as follows. Percent error equals the measured value, which is what you get when you do the experiment, minus the expected value, which is what you actually should have gotten, divided by the expected, and then times 100. Okay, a couple of other things with this. First one, you are accurate if the percent error is less than 20. So if the percent error is less than 20, you're accurate. That's how you know. So if you get a percent error, it's lower than 20%, you're good to go on the experiment. If it's more than 20, then you're not going to be accurate. And we're going to have labs where it's more than 20. Okay? There's one lab in particular when we get into energy that your values are going to be terrible. Okay? And then we have to figure out why are they bad and how do we fix it, which we will. Okay? But your percent error needs to be less than 20 for you to say that you're accurate. So if you do an experiment, it's more than that, you say, we were not accurate in this experiment. The second thing to keep in mind is negative percent errors are fine. So when I say less than 20%, I also mean less than negative 20%. So as long as you're between negative 20 and 20, you're fine. So 19% is fine, 3% is fine, negative 15% is fine. All of those are fine. You just got to be in that range. Just got to be in the less than 20%. That's less than positive 20 and less than negative 20. And by less than, I mean closer to 0. I know technically that's bigger, but in physics we don't necessarily think about negative numbers the same way that we do in math, and we'll get to that pretty soon. But negative numbers work a little bit different in physics. So usually when I talk about smaller negative numbers, I'm talking about closer to 0. But again, we'll talk about that. Okay, any questions about percent error for me? Woohoo! Go to the back. Look at us, we're almost done. All right, using our data, how do we determine if we're precise? This one's pretty straightforward. You look to see that your trials are consistent. And when you're doing that, you should do at least 3 trials. You should do at least 3 trials. Ideally, you can do more. We will not frequently do more than 3. The reason being, very simply, we don't have time. If we had time, we would do more, but we don't have time. So we'll just do 3 most of the time. But you can look at your 3 data points and see, are they consistent with one another? If they are, then you can say we're precise. If they're not, then you would say that you're not precise. This is not the ideal way to do it. It's fine. There's a better way to do it, which we'll talk about in a second. So using a graph, how do we determine if you're accurate? So if we have a graph like we did in the last lab when we did the bouncy ball, or we did the bouncing, how do we know if we're accurate by looking at the graph? The way we can do it is 2 things. The first one is, does it fit the expected shape or pattern? Does it fit what we expect it to fit? Does it do what we expect it to do? Great example. In a couple weeks, we're going to do these labs with these cars I have over here in this bucket. One of the cars is constant motion, one of the cars is accelerated motion. Do the graphs show that? Because if the graphs don't show that, then we're not accurate. But if they do show that, then we can assume, partly, that we are accurate. Okay? So that's one way we can figure out. And the second one, does it pass through any points we know must be accurate. A great example, sticking with that car lab example, we know that at 0 displacement we should have 0 time. So if we get our graph to go through 0, 0, we can assume that's fairly accurate. If it doesn't go through 0, 0, then it depends on how far off it is. Is it way off of 0, 0? Is it kind of off 0, 0? Where is it? And that is another way to figure out accuracy. Okay? Both of those ways are okay. The percent error is the better one. Percent error is the better one for figuring it out. But you can do it this way as well. Frequently, this is the way we'll do it because we don't know the exact correct value. I don't know how fast the cars are supposed to go. They're all different varies of batteries. They all have different various levels of the batteries being drained. Each car is a little bit different, so I don't know the exact number they should be. So we're going to check and make sure our graph makes the pattern it should make. Okay? Number 7, using a graph, how do we determine if we are precise? Like this. So here are my data points. Okay? We make a fit line that follows through those data points. What we're looking for is, are the data points on or consistently near the fit line. So, are the data points on or consistently near the fit line? This example, you can see my data points are kind of close, but they're kind of all over the place, right? We got 3 that are too big. We've got 1 that's a little bit too small. It's not quite exactly where it should be. I didn't do necessarily a particularly good fit line. So it's how close are you to what you should be, like how close are they to each other on the line? The line represents the average of what we think we should be getting. So how close are we getting to the average of what we think we should be getting? Okay? So if we calculate the slope to be 2 over 1, then we would have up 2 over 1, up 2 over 1. So we would expect to get, for 2 seconds of time, we would have 4 meters or something like that. So are we getting close to that? Or are numbers inconsistent with that value? This is the best way to figure out precision. Accuracy just depends on what values you have. Precision, ideally you graph it, because that's the best way that you're going to see it, is if you're graphing it. Okay? So that's the best way on that. And we already talked about 8. Look at this. We survived. Any questions on accuracy versus precision, how we figure it out, how we calculate it, anything like that? Perfect. Okay, what we're going to do here for the last bit of the period, for the remainder here, and we got plenty of time, we're doing great.